Okay, so since most of us do have wireless local area networks, familiar with it on our scale. When we're talking about these wireless local area networks, we've talked about in the first chapter some other things like a wide area network, a metropolitan area network, local area network, and a personal area network. Personal area network, something like this Bluetooth, wireless, what we use for our access points to connect machines. In a lot of cases, telephones, if they're in LAN mode, or tablets, those kinds of things for short distances. The need for sources of wireless networking standards. Why do we need standards? So they'll all communicate. Back to, what does the Wi-Fi organization do? They kind of ensure standards. They certify devices. They certify the devices meet standards. When we started in all of the networking, all of the computer stuff, back when, a long time ago, what, in the 80s, 90s, 80s, there was a lot of stuff that was not compatible with other stuff. At one time, if you bought a Dell computer, you wanted a video card, you bought a Dell video card. Same way with Apple still, isn't it? How many people make stuff for Apple devices? It'd be like Apple. When we first started out, and we talked about earlier with wireless, if you bought a D-Link wireless card, you better have a D-Link access point because they didn't meet the standards. So the standards allow all of these devices to interoperate. And that generally means we're going to lower the price for us because you get more people competing for your dollar. So we do those things. The features of the 802.11a, b, g, and n WLANs, I'm going to go through those briefly. We'll hit the highlights, and the details are in that 600-page document, the wireless standard document. Different types of client hardware and software. Probably nothing really magical there. We'll go through, and they got a bunch of pictures in the book. Most of the, I guess all of the laptops, really, probably all, although I hate to use all on anything, have wireless cards in them. Number of desktops are coming with wireless cards. You got to be careful with the desktop because of the location. If you put it in one of these nice, in between all of these really nice desks here, blocking all the access, you're not going to go very far. We'll talk about those kinds of things in the antennas next week. Different functions of the infrastructure devices. The objectives here. So the standards make it easy to purchase and use a wide variety of products. Without standards, they're just not going to work, except proprietary to proprietary. And that's what proprietary devices are about, and that they only work with my stuff. Some people want it to be proprietary so that it only works with their stuff, so then you're forced into buying things from them. Standards are based wireless technology is based on standards to help ensure the different products from the different vendors in the same function, in the same capacity, same thing we've talked about before, that they'll work. If I go buy a D-Link card, it will work with my Netgear access point or my Linksys access point. When we get into lightweight access points, when we get into the access point area, with the wireless LAN controllers, generally it's going to be proprietary. There aren't any real standards established there, so they're probably not going to be compatible with each other. That's on a much larger scale than we normally operate. Telecommunications would be essentially impossible without standards. It's kind of like languages, the way I think about it. If we all spoke the same language, we'd all understand each other. We all speak the same language, English, right? Or some form of it. Mine's sometimes questionable, but we speak English. What if somebody came in here, sprechen Sie Deutsch?
German.
Sprechen Sie Deutsch?
Can't speak German.
Can't speak German. Wouldn't be a very good conversation. So if somebody makes one standard, somebody else makes another standard, communication is going to be non-existent. Interoperability, competitors, and all the things we've talked about. Competition, why does you ever looked at the price of a Mac laptop? How much? $800? You found one for $800? I've never seen one under about $1,200, $1,500. Yeah. Yeah. Huh? They're expensive. What was an IBM PC? Laptop cost. $3 or $4. I saw one advertised $299 this weekend. It had a 15-inch screen.
It's a 15-inch?
Yeah.
For $299?
Yeah.
Wow.
Probably Walmart.
I'm seeing $1,200, $1,500.
For Macs. For Macs. And that's the lowest you're going, right?
Yeah, that was 26.
26.
Almost 5,000.
5,000.
6,700.
Why? They meet a standard. Whose standard do they meet? Theirs. Who can make products that work with Mac products? Mac. Apple. How many people make IBM PCs? Oh, you got Acer, you got HP, you got Compaq, you got, who's the company that used to be IBM? Yeah. IBM doesn't make them anymore. They spun that company off. But lots of people. So why does it cost $399 for an IBM PC compatible and $1,200? The cheap one, $1,200 for the Apple. Competition. Any vendor, and if we meet the standard, any vendor can do that. So you got to build them to standard. I'm not trying to belittle Macintosh or Apple products, because the one thing they do is they work the way they say they're going to work. Why do they do that? Because they control the whole product, and they can make everything work better than trying to somebody makes the video card, somebody makes the memory, somebody makes the motherboard, and then you marry all that. Is it going to work? To do that, we need the standard. To make all of our wireless devices work, you need the standard. And we always go to backward compatibility, right? The 802.11g access points are backward compatible with 802.11b. The one thing you're going to find is not compatible is A and B devices, because A is an entirely different everything.
I'll be here this evening. I was off today.
Entirely different everything. Different frequency, different multiplexing, different configuration. So A's and B's are not going to be the same. Well, look at 802.11n. What about it? Is it backward compatible? With G? Yeah. Does that impact the newer standard? Yeah, because if you, back to the G, if you get an 802.11g and you put it in compatibility mode where you can use both A and B devices, somebody comes with a B device and says, oh, you want to be a B? Okay, we'll go at B speed. So it's going to slow things down. There is compatibility, but if possible, you wanted to operate them at the standard they were designed to be run at. Advantages, lower cost, help create a migration path for equipment upgrades. One of the things that we didn't have that equipment upgrades was they upgraded WEP to WPA. Made it a little bit better, so that the B devices could work with that. WPA2 is an entirely different set of hardware. You can't migrate, you can't use that particular security configuration on the older devices. You have to buy new hardware. But going from a G to an N, compatibility upgrade, can we upgrade some of our machines at the same time and still keep them running. And that's what we're really talking about there. You don't have to go out and throw a whole bunch of new hardware into it. So that's one of the things the standards are going to help us with. Newer standards generally backward compatible, and in the G and the B it's backward compatible with the exception of the security. If you wanted to use a B device, a secure B device on a G, you had to use WPA and not WPA2 in that standard. De facto standards, common practices range from ease of use to tradition of the majority of users, usually established by success in the marketplace. De facto standard. The de facto standard for intrusion detection systems is SNORT. It's the de facto standard. Is it the standard? I think probably the de facto standard for sniffers is maybe a Wireshark. Why? It's easy to use, free. Don't have to go buy it. Easy to install. It installs on any platform you want to put it on. It's the de facto standard. It's not an official standard. It's not written by the IEEE or somebody like that. It's just something that we all use that. De jure standards are official standards, and these are here because these are really great test questions, right? De facto standards and de jure standards, official standards, controlled by organizations, the IEEE, those types of organizations would create those standards. And the process obviously can be very involved. Consortia created standards, usually industry-sponsored standards, and they may just apply to a portion of the entire universe of those things. To develop a standard that promotes the organization's specific technology. Got a little bit of time. So somebody is trying to get you to buy theirs. They have a standard. All of their stuff is compatible with the standard. Types of wireless LANs, there's more to that. This is a table of the technology, the frequency, and the maximum data rate. 802.11a. A and B were actually created at the same time. 802.11a is 5 gigahertz unregulated band. 802.11b is a 2.4 gigahertz, but the speeds were radically different. 54 meg for 11a and 11 meg for 11b. 11a never really took off. Well, that wasn't the issue. Well, it couldn't go that far. That's true. The higher the frequency, the shorter the range. That's always going to be the case. But the real reason that the A didn't take off, because it had some real advantages in business, didn't it? 5 times faster. We had to get to G before we got to the 54 meg in the 2.4 gig range. The hardware is different for A and B, and to make the chips, they ran out of silicon for the A-type devices. They never really got into the manufacturing process for a number of years. And by the time they could make the devices, too many people had the B standard installed. And even at a frequency, the way that the signals are formed are different, but frequencies 5 and 2 are not going to be compatible. Get down to 802.11n, it's got both, 2.4 and 5. And when we talk about mesh networks, wireless meshes, you're probably going to have both frequencies. One of the frequencies, the access points might talk to each other with the 5 gigahertz and talk to the clients with the 2.4 gigahertz. So you can have both of these things. So the N's got the 2 and the 5, can be 2 and 5 selectable, or 2 and 5 concurrent. You can have both of them at the same time or one at a time. Several amendments, the D, the H, and some others. Current standards 802.11, 2007, and one amendment, the 802.11n, 2009. If you go back, we have the amendment. The amendments to change the standard. So what they did in 2007 was take all of these recommended changes, all the amendments, and rewrote the entire standard so that you had a standard without the amendments, that it was a standard. And then we've got the G amendment, which was adopted in 2009. Combined all the standards, officially retires all the previous standards, still refer to them individually, still common to refer to them individually. So they combined all of the changes into one document. And now since then we've had the one change to add the N standard to it. Technical corrections. 802.11 was the original wireless, and it was 1 megabit per second, 2 megabits per second to take place via infrared IR. IR, not such a good thing. What's the problem with infrared? Line of sight. Well, that's what wireless is, isn't it? Line of sight.
Wireless? No.
It's not?
I don't think so.
You don't think so?
No, how does it go to the walls and the floors and stuff?
Ah, that's different. Still line of sight. It's just which line of sight, isn't it? Not line of visual sight. Will it go over the horizon?
I don't think it can go that far.
I don't think it can go that far. What if it could? We'll get into those things a little bit later. But the line of sight, you've got your electromagnetic line of sight and a visual line of sight. He's absolutely right. Our problem won't go through walls, go through windows and things. Bounces around. It is very short range and not used very long. A long time ago I had a laptop that had an IR. The only thing that I ever had that had an IR connection on it was an old telephone, an old cell phone. And had this discovered accidentally this old laptop that had an IR connection so that you could upload and download stuff from the telephone using it. Didn't have to go buy any other adapters to do that. That's probably what we would use those things for. Infrared, send data by the intensity of the infrared light, the light spectrum, all of them infrared. Do any of you use infrared devices? Remote control. I used to have an infrared headset. Wouldn't go very far. You talk about short range. It was short range. It was probably about 15, 20 feet. Hmm? Yeah. Yeah. But they are there. I don't know how many people are making infrared devices anymore. 802.11 infrared, directed transmission and diffuse transmissions, and rather than talk about them, the easiest way is to look at them. Directed transmissions, a line of sight. Device to device, and again, this is not going to be a very long distance. A diffused would be in a building like, in a room like this, where you would actually bounce it off the ceiling or off the walls in order to get the signal where you wanted it to be. These are very low speed, very short distance, probably not manufactured anymore, wirelesses. So limitations, lack of mobility, limited range, confined to indoors, low transmission speed. It would be confined to indoor, wouldn't it? What if you went outside with in the bright sunlight with your infrared transmitter? Sun would walk all over it. I can tell you for a fact, I had a television one time that set facing, and I guess it was in the morning, the sun would come up in the window, and the sun would get on that receiver for the remote, and it just start going around the channels. Couldn't stop it.
Oh man, that's funny.
Yeah, I mean that's what it would do. That's what infrared will do for you too. So we really want to use electromagnetic, the stuff we talk about, the A, the B, the G's, and the N's, are the things that we want to be able to do. Radio, James said, penetrate objects and provide us the mobility. We're not limited to inside, outside, because we can have outside wireless. Travel longer distances, can be used in and outdoors, can travel at much higher speeds than infrared transmissions. the 5 gigahertz, why was it so much faster than the 2.4 gigahertz? Higher frequency, higher data rate. Higher frequency, shorter distance. They have, in the Navy, a real problem, because we have absorption, and that's one of the terms that you got to know about. This real problem with communicating with these submarine kind of things. Because when they go into the water, they're under the water. It's tough to communicate with them. They have an extremely low frequency communication system that will penetrate the water. Extremely low data rate. The lower the frequency, the longer the range. Just like the shore, and absorption changes too. High frequencies really are susceptible to absorption.
That's why a whole lot of routers looking out like dual band now.
Yeah, well, the dual band routers are the ends. The dual band are the A and the G standard on them. So you can use both frequencies, that A and the G, the 5 gigahertz and 2.4 gigahertz. That's part of the 11N standard. 11A specifies the use of OFDM technology using a 5 gigahertz, and we'll talk about this stuff later on. In the uni bands, that's the name of them. There are 3 separate bands for these things. Obsolete, the standard itself is rolled into the 802.11/2007. We'll still continue to probably call it the A's and the B's and the G's forever, but they're all now part of the 802.11/2007 standard at that frequency. This over here talks about subcarriers. One of the things that made it more efficient was it had subcarriers or subfrequencies within it. 11B, HR is high rate, DSS, direct sequence spread spectrum, something I always have trouble saying. Different from frequency hopping spread spectrum, which was the original standard. 2.5 gigahertz, backward compatible with DSS, and again, it's obsolete. It's rolled into the 802.11/2007 standard. All of these things will be. This picture here just kind of shows the frequency hopping, and it moves around from frequency to frequency. The spread spectrum technology was something that worked pretty well for communication in World War II. And we used to use it. I think the Army used it for a long time. The problem is that the receivers got a lot better, and now instead of jumping around and having part of the conversation, direct sequence is part of the intelligence is on different frequencies within a band. The frequency hopping just goes from frequency to frequency based on a programmed pattern. But the receivers in the Navy, we have one called a Slick 32, just received everything at the same time. So you get the whole of the conversation regardless of what you were doing there. 802.11 was 2 megabits top end. The B amendment added 2 higher speeds, 5.5 and 11, to the original 11 standard. ISM is industrial, scientific, and medical ISM when you see the ISM band. Unregulated band, it's something that anybody can use, anybody can make devices to work in those frequencies. It's not regulated by the FCC. Supports wireless devices up to 107 meters, 350 feet. Radio waves decrease in power over distance. Nothing really magic about that, and they do. They decrease, attenuation. As you get further from the access point, your data rate's going to go down. The 54 megabits per second is usually going to be within 30 feet of the access point. If you get out at the 107 meters, you're probably going to be somewhere around 2 megabits per second in some of those standards, depending on which standard you're in, obviously, and you'll have to determine that based on what's going on. The picture at the top here is the 802.11a, or not A, BG standard, the 2.4 gigahertz, and it shows the 3 channels. There are 3 distinct channels, 1, 6, and 11. The bandwidth, and here's a different way of talking about bandwidth. Bandwidth we always talk about, and we're really talking about data rate, how fast we can go, what's our bandwidth. We're really talking about throughput or data rate. The bandwidth is actually the difference between the high and the low of a frequency, range of frequencies. So the bandwidth of these things are 22, the distinct channels, 22 megahertz. You need a 20 megahertz channel in order to get all of the data on it. These things are designed to have 1 megahertz on each side as a buffer. So when we put the ones together to get the distinct channels, the channels are 22 megahertz, 20 megahertz for data, 1 megahertz on each side. But if we don't separate them with the 1, 3, and 6, you're going to get overlap, and you're going to get interference from the data itself. This is a picture here just to kind of put that in your mind. When you see STA station, it's any wireless device, not an access point. Something that's going to connect to an access point. It's called a stay. Other factors determine the speed include the number of wireless devices in the network, the obstructions between the devices. If you go on, if we had a mirror in front of us, is it going to go through the mirror? Probably not. It's probably going to bounce off of it, isn't it? So what's there? What's the material? And later on when we talking about wireless surveys, what kind of material? It'll go through sheetrock pretty readily, but it's not going to go through, and if you go in this building, it goes in the main part of the building pretty well, but if you go on the other side of the break room, there is a physical firewall there that's got a lot of rebar and those sorts of things in it. You have an awful lot of problem. They put an access point back there. We have an awful lot of problem trying to connect to an access point from here to there. It's one of those that you can kind of see the signal, but you can't get a very good data rate to go through it. Data rate and throughput. The data rate's a theoretical maximum, and the throughput's what you're actually getting. So the data rate would be 54 megabits per second. 2 megabits would be what I'm actually getting. That would be my throughput as I get far away from this thing.
I still think ISP should give you credit for the difference.
Yeah, well, that's up to you and them. The 802.11 standard specifies a maximum of 54. Also supports 48, 36, 24, 18, 12, 9, and 6. These are going to be, as you get further away, as the signal varies, these are going to be the speeds that it locks into. So as signal strength varies, we're going to get one of those speeds. Here we go. The A and the B were published at the same time. A came to market later due to technical issues, couldn't get silicone, and higher production costs. It did cost more to make the devices than it did. Not long after that, when they started making them, they made for a while a number of A and B dual devices. And they still, I think they've gone back to making some of them now. But typically businesses would prefer the A because it had a shorter distance. Do they really care about the shorter distance? It can be advantageous because if we had a shorter distance, what's that going to mean? Somebody going to have to get closer to get their map. The higher data rate. So generally, in that sort of world, it was everybody. I think all that I've ever had, I almost bought an A and a B card one time, but it's been B's and G's and M's. Range is less, typically no more than 100 feet apart. The G, the ERP is the extended range physical, which is some we'll talk about when we get to the physical layer, but some things that is done to make it go a little bit farther. The use of OFDM technology, the 2.4 gigahertz, the G, the ISM band, and offers backwards compatibility, HRDSS and DSS. That means that we're backward compatible with the B standard. HR is high range DSS, and again, all of these are obsolete rolled into the 2007. H is transmit power control. You have to have that in some areas. One of the problems that happens with A is it can interfere with radars. And they have specified power levels that can happen. The transmit power control allows the system to self-regulate to the power. It all has dynamic frequency selection so that it can select the best frequency for these things. Uni-band spectrum management enhancement, and again the uni-band is, when we see this, uni-think 11A, or what used to be 11A is now part of the 5 gigahertz frequency when we do those things. This one gives you an idea of the, says G, wireless G high speed and wireless N for these different speed ranges. The 5 times faster, the G 5 times faster than the B, 8 times faster for the wireless G high speed, and the N's 12 times faster. So as the standards change, and improvements really are being made in both security and in the speed that they support. G only, B only. Devices are recognized, and the G devices, are ignored if we only do B. This is, I think, the important one. In mixed mode, although 11B and 11G devices can function together on the same wireless network, the presence of any B device will cause the network to decrease its data rate to the B speeds. So unless you really need it, don't set your access point up in mixed mode. Set it up in G if you're using G devices, because if anything shows up at the B standard, it's going to decrease your throughput and your data rate. 11N, up to 600 megabits per second theoretical. And again, we talked about this earlier, James, that 300 megabits per second is the practical one that's being built right now. The 600 megabits can be, but based on everything that I've read, up to this point, nobody's making the hardware that supports the 600. But that would be 600 megabits per second wireless would be pretty good. It's not gigahertz or gigabit, but it's getting a lot closer than we've ever been before. And it operates in both the 2.4 and the 5 gigahertz bands. Using MIMO, multiple input, multiple output, we can have multiple connections at the same time. Technology, and this little picture over here shows MIMO, MISO, multiple in, single out, and CMO, single in, multiple out. What kind of connectivity, and the one, it's got everything bouncing around, and we'll talk about that a little later when we talk about the physicals, multipath, multi-direction. Multipath is a really bad thing in everything until you get to N. N takes advantage of the multipath in order to find the best signal and sometimes amplify the signals. Up to speed up to 600, I think we've already kind of talked about that. Double the indoor range and triple the outdoor range in these things. Uses different frequencies to reduce interference. It's called frequency diversity. What it'll actually do is, if it gets multiple signals, we'll pick the strongest signal and then answer on that particular frequency and path. The hardware, different types, and we got Nick here's got 2 antennas that will go into a desktop, a laptop connection, and a USB connection. So you can get the wireless cards in all different varieties. Typically what we're going to have is one that's installed in our laptop. NIC, nothing magic about NIC. Been there, done that, seen those. Network interface card, wired, wireless, typically going to be on the motherboard itself. Different cards, USBs. The USBs look very similar. If you haven't seen one, held one, done one, look very similar to just flash drives. Cards for portable devices, all sorts of different ones that come in these things, large form factor, PCMCIA. I think that you can still buy these things, but I don't think they even put the PCMCIA slots in machines anymore. I really, in card bus, I haven't seen those. I really think that if you're going to go get an external device, your wireless card burns up in your laptop. What are you going to do? You can throw the laptop away or put one of these types of devices. A USB is probably what you're going to do with this, because you're probably going to find that you don't have a slot for anything else. Small form factor, and this is some pictures of what some of them look like. The internal cards, and what these machines that you're using in here have are the PCIe, the PCI Express in there, and in the card is actually a card that's on the motherboard, on the card, on the expansion card, and what you see on the surface is the antenna. So the antenna is the one that actually, that device there is the antenna. Utility software, wireless NICs can be part of the operating system, and I think that's what most people use. Third-party software, if you get a wireless card, it's probably going to have software that goes along with it to manage it. If you buy a laptop, I bought an HP, it's got the HP management software. You can use either. The first time I got a, what did I get? Toshiba, it had theirs in it, and I wanted to get rid of it. It's tough to get it out. Finally called them up, and they said, oh, just delete the NIC and redetect it. It worked just fine. It came back with a standard operating system configuration. So these programs can sometimes tell you a little more than the operating system. Wireless zero configuration is a management utility that was introduced in XP, makes it easier to connect to wireless, more automatic. Huh?
Service Pack 2 or?
Yeah, Service Pack 2, I think. Determines which wireless network to connect to based on the default settings or preferences set by the user. It's in Windows 7. It's something that we have. It's the thing that allows you to just go and connect to the network. Also, as an, oh, by the way, if you use 802.1x wired, this has to be running, which is kind of odd that you have to have a wireless service running to use a wired service. WLAN auto config replaces the wireless zero config in Windows 7. It's same functionality, different process of these things. Infrastructure devices, access points, bridges, gateways, power, Ethernet devices. Access points, we all use those. Bridges, what a bridge typically does is connects two wired network segments together. When would we want to do that? Let's say that Skyline grew logarithmically and they had to go over here and lease this theater.
You don't want to run a cable, so
you don't want to put on a cable because one city probably not going to let you. You don't want to dig up the parking lot, so what's the convenient way to do that? A wireless from the two rooftops to connect the two wired, and then you would still have control. You have a wired network over there, a wired network over here. The two access points connect the wired networks together. Gateways. Gateway is a fancy name for a router. So what you're probably using at home is not an access point, but a gateway, because you're using a router probably, right? I am. An access point is just that. You plug it into your wired network. It doesn't route. It connects wireless devices to your wired network. Power over Ethernet devices are typically going to be a switch, a PoE switch that has power on it that powers the devices. So when we get remotely, we don't want to have to worry about plugs and power sources. So you can do it with power over Ethernet. And if you look around here at the phones, take a look at some of these Cisco phones. Do you see a power cord on any of them? They're all power over Ethernet devices. There's a PoE switch in the knob. What do you think would be the issue with a power over Ethernet switch? How much power does it take to run a power over Ethernet switch? You need to be careful of that. Frequently, a standard 15 amps, pretty standard service in it. Probably not going to be enough, so you got to be careful about where you plug it into, so that you don't knock everything else offline, because it does actually provide the power. What if you plug a non-powered device into a power over Ethernet port? Burn it up, right? Now it actually checks before it sends power. It checks to see if it wants power. So there is a process that it determines whether it's a powered device or not. Access point, antennas, bridging software, and an RJ45. Again, what we have is we plug it into our wired network. It extends the wired network. We just actually put it on the wired network. Access points, and I guess you can only say that sometimes. Autonomous access points. Autonomous and lightweight access points are the two kind of major classifications. Autonomous is an independent. We can put on security, manage it individually. Also call a fat access point. Disadvantage is if we've got 30 of them and we want to make a change, how many are we going to make changes to? All 30 of them. How long is that going to take? A long time. Lightweight access points, thin access points, and interestingly enough, if you upgrade an autonomous access point, you upgrade it to a lightweight access point. Lightweight access point doesn't contain any of the management configurations. They get sent to it by a wireless LAN controller that you manage, so that if you make a change to the wireless LAN controller, it gets sent to all of the access points. The autonomous does things to have intelligence to manage authentication and encryption, so that you would actually authenticate to it, or some form of it. You might have an 802.1x, you might have a radius server or something else. The lightweight access points, all of that's taken care of by the wireless LAN controller. You got to have wired infrastructure in order for that to work. So you have to connect to those things. The wireless LAN controller, WLC, distributes the information to the lightweight access points. Remote office WLAN controllers manage multiple wireless LAN controllers. So we have the LAN controllers, and if you got a lot of those, we're getting to a really big wireless network now, aren't we? Because you got too many wireless lightweight access points for a single LAN controller to manage. So we have a WLAN controller, remote office WLAN controller, to control the switches here to control the access points on down the line. Some places have really big ones. Disadvantages: don't provide integration of wired and wireless networks. And here's the big one: devices are proprietary. What this means is that on the lightweight access point, you only got wireless. You only got wireless connectivity. And they are proprietary, so if you're going to use these things, if you start with Cisco, stay with Cisco. If you start with somebody else, stay with somebody else. This is just a kind of a diagram of how it would be. We've got the WLAN controller up here, where we put all of our configurations, gets sent to the lightweight access points, and then the laptops connect to it. The lightweight access points and the wireless LAN controller are all connected to your wired infrastructure. Again, I keep saying that. The only time you're not going to need a wired infrastructure is if you have a wireless mesh. And those are usually self-healing. They'll automatically turn them on and they just start talking to each other. They find the best paths themselves. Communicates with the mesh, communicates with the next closest access point. Create dozens, even hundreds of mesh access points. You only got to have one device that's connected to your wired network that way. I think the issue with that would be it's going to be really slow, because as you go from access point to access point to access point, if you use a wireless amplifier, if we're going to extend the distance, you're typically going to have the speed, because you have to, until we get into the later standards, you have to acknowledge receipt of every packet, which really slows things down. Backhaul connects the mesh to the mesh access points to an internet connection. This is what we have out here. They're showing wired. These connectivity are not wired. This is actually a wireless connectivity. I guess they should have used little lightning bolts on that, but the access points are connected wirelessly. We only have one of them that's connected to the wired network. Advantages: low cost, large coverage, easy to change the coverage area. If we want to extend it, we just put in another access point and it'll automatically come online in that wireless network. Self-configuring, self-healing, fast installation. So when you want to put a network up real fast, it's kind of like golf tournaments. They do. IBM always puts that. They always talk about IBM has installed the network there, right? What would allow you to put a network in really quickly? Something like that. Sometimes they just take the whole package with them driving the trailer, but you could put a network in, larger area network in relatively quickly, and we'll get into the channelization in a later chapter, how you're going to connect these things, because I spent a lot of time saying that they interfere with each other, and they do interfere with each other. Bridges, put a little picture here, lightweight access point to wireless LAN controller, and here access point to access point is going to be the bridge itself. The bridge typically is going to bridge two wired connections, two wired access, two wired networks. I'll get there in a minute. Two or more wireless, on and on. And these can be either the short range that we've talked about, or you can have a longer range. What if you were going from, I don't know, from here to downtown? We're not high enough, we'd have to build a higher bridge. As long as you've got an electromagnetic line of sight, they'll have any interferences, and we'll talk about some of those later on. We could connect our two networks together without paying a provider or whatever else. Some people want to do that. So those are things, and on those you can have point-to-point or point-to-multipoint, whichever way you want to do it. Better picture here, wireless workgroup bridge, access point to the wired network, connects, again, here we've got connecting two wired networks. We're going to have a very big one up here, just the file server, but connect two wired networks using wireless devices. Point-to-multipoint, point-to-point the other one. Two ways, a root bridge can only communicate with other bridges, a non-root bridge can only communicate with a root bridge. What that means is once you configure them that way, they're not going to talk to each other. You're not going to connect wireless devices, phones or tablets or laptops to those. They're only going to talk to each other to relay the signals from the wired networks. Repeater mode, extend the distance, placed between two other bridges. Repeater mode is probably something that's going to slow you down, because you have to, as you relay the information, you have to acknowledge it each time. It's going to reduce the speed. Access point mode, so these are going to be the modes, and those Cisco APs that we have these modes: access point, repeater, root, and non-root, in order to create a bridge from those things. Gateways. We decided a gateway is really a what? Just a router. Enterprise, encryption gateways, and residential WLAN gateways are the ones that are there. So we're going to maybe use those things in order to do that. And I think probably everybody's done those, haven't we? Windows Connect now. Soft AP, and they got, I think in this chapter there's a couple of soft access points labs for you to do. He's supposed to be adding you guys to the group. Power over Ethernet, we've talked about that in networking and a few minutes ago. All it does is send the power over the device itself. You've got to Be sure you got enough power. You got to have power PoE devices. What you don't have to have is the ability to actually plug the device in. It's kind of handy for telephones because when you take them to the offices, you don't have to worry about a power supply or any of that other stuff or a plug to plug it in with. The thing that probably would be really handy with is that what if you put access points in the overhead? Where's your power?
Over Ethernet.
Power over Ethernet. Power over Ethernet, the source equipment, and injectors. But the injectors are, if you don't have a PoE switch, then you can put a power injector in the Ethernet system. Thought I wasn't going to get there, didn't you? Why we need standards? Or do I have to start over?
So they can be compatible with each other.
So be compatible with, and that's really what it is, isn't it?
Yeah. Makes
Makes it cheaper for us. It really does. I think it does. Because if you have a standard, then who can build the product? Anybody can build to the standard. Kind of like car parts, third-party car parts. What makes them fit? A standard. I mean, if you're going to get a water pump, it's got to be so deep, it's got to have so many holes in the housing and that kind of stuff. That's going to be the standard. Wireless device is going to be the standard. It's a different kind of standard, electronic standard, but that's what we're going to do with them. Access point is a base station. When we get into these things, we've got the AP, the access point, and the STA, the stay. The STA, the station, is going to be anything that connects to an access point. Mesh networks, advantage to those is we can put them in pretty fast, can expand them really quickly. They can be self-healing because they are mesh. One of them goes down, it just finds the next closest neighbor and sends the traffic that way. A lot of times the mesh networks are going to have both 2.4 and 5 gigahertz. The 5 gigahertz might be used for the access points to communicate with each other, and the 2.4 gigahertz to connect with the stations that are on it. And a wireless bridge connects two wired segments. Building to building, if you've got multiple buildings, you may want to do that with your network. And gateways we determined are simply routers. Two different terms. A lot of this has two different terms in it, just like bandwidth. What does bandwidth mean? It depends on how you're doing it. Is it data rate or is it actually bandwidth? The high and the low, the difference. How much of the frequency band do you have? Questions? I know you just want a break. Let's take a break.